Welcome to the deep dive. Today, we're asking something that sounds, well, pretty basic. How much does our own galaxy, the Milky Way, actually weigh?
It does sound simple, doesn't it? But figuring out the mass of the Milky Way is honestly one of the trickier puzzles in cosmology.
And it's not just about, cosmic trivia. Knowing this mass is really important,
Oh,
right?
yeah, absolutely. It's fundamental. It affects how we understand the whole history and the future of our local group of galaxies. Think about our interaction with Andromeda, for
The
instance.
collision course we're on.
Exactly. Mass governs that gravitational dance. Plus, it tells us a lot about how galaxies form and grow within the larger cosmic web structure.
So, knowing the Milky Way's mass helps us place it. Are we average? Heavyweight? It lets us know if what we learn here applies elsewhere.
Precisely. Is our galaxy typical or maybe a bit unusual? And for you listening, our main focus today is how this incredible mission, Gaia, is giving us, well, really powerful new tools to tackle this very question.
Yeah, because even after decades of work, the estimates still seem to vary quite a bit, which is fascinating in itself.
It is. There's still a significant range, so let's get into why it's so difficult.
Okay, where do we start? We can see stars, gas.
Yeah.
Can we just add all that up?
Well, we can, and we have a pretty decent handle on that part. The baryonic components, that's the stars, the gas, the dust, even the supermassive black hole at the center.
But that's not the whole story. Not even close, right?
Not even close. The vast majority of the mass, maybe 80 to 90%, seems to be locked up in this enormous invisible halo surrounding the visible galaxy. And that halo is dominated by dark matter.
Ah, dark matter, the usual suspect.
Yeah.
Invisible, doesn't interact with light. So you can't just see how much is there.
Exactly. That's hurdle number one. You're trying to weigh something you fundamentally cannot see directly.
And hurdle number two seems to be defining what the galaxy even is in terms of its edge. You mentioned virial mass.
Right, that's another challenge. Where do you stop measuring? The virial mass is kind of a theoretical boundary. It's defined based on how much denser the galaxy is compared to the average density of the universe.
So it's not like a sharp edge, more like a fuzzy boundary where the galaxy's influence peters out.
Kind of, yes. It depends on that average density contrast. So defining the volume we're measuring within is itself part of the problem.
Okay, so you can't see most of the mass,
Yeah.
and defining the edge is tricky. How do astronomers actually try to weigh it then? You mentioned tracers.
Yes, tracers are key. Since we can't see the dark matter, we watch how things we can see are affected by its gravity.
Like what sort of things?
Things like individual stars orbiting way out in the halo, globular clusters, those are dense balls of stars, and even entire dwarf galaxies orbiting the Milky Way.
Okay, so their orbits are dictated by all the mass inside their path, including the dark matter.
Precisely. If you can measure how fast these tracers are moving and how far out they are, you can infer the total gravitational pull needed to keep them in those orbits. And that tells you the enclosed mass.
It's like watching planets orbit the sun to figure out the sun's mass. But I guess it's harder for galaxies.
Much harder, partly because of another big limitation. We often only get part of the picture of their movement.
How so?
Well, using the Doppler shift of light, we can measure their line of sight velocity pretty well, how fast they're moving towards or away from us.
Okay, that seems useful.
It is, but ideally, we need their total space velocity. That includes the motion across our line of sight, the sort of sideways movement. That's called tangential velocity or proper motion.
And that sideways bit is harder to measure.
Historically, yes, especially for faint, distant objects like halo stars or dwarf galaxies. And this leads to a problem astronomers call the mass anisotropy degeneracy.
Okay, break that down for us. Degeneracy sounds bad.
It just means there's an ambiguity. Anisotropy refers to whether the orbits are more radial, plunging in and out, or more circular, tangential. Without knowing the full 3D velocity, you don't know the shape of the orbits.
And why does the orbit shape matter for the mass?
Because a galaxy with a certain mass could produce the same observed line of sight velocities if the stars have, say, mostly radial orbits, or if it has a different mass and the stars have more tangential orbits. You can't easily disentangle the mass from the orbit shape just using line of sight speeds.
So you had to make assumptions about the missing sideways motions, and those assumptions could throw off your mass estimate.
Exactly. That degeneracy was a major source of uncertainty in pre-Gaia mass estimates.
So speaking of pre-Gaia estimates,
Yeah.
what kind of numbers were people getting back then, say, using those halo stars?
Well, studies using the kinematics, the motions of halo stars often pointed towards somewhat lower masses, typically less than about 1 trillion solar masses, maybe like 10^112 Amenia measured within a standard radius.
And the limitations were the lack of those tangential velocities and maybe not having huge numbers of stars?
Both, yes. Limited proper motion data and needing to extrapolate from the stars you could measure out to the galaxy's edge.
What about using the satellite galaxies or the globular clusters before Gaia? Did they give similar results?
Those tended to give slightly higher values, maybe more in the range of 1 to 2 trillion solar masses. But there's a catch.
Which was?
A lot depended on whether you included certain objects, like the dwarf galaxy Leo stirred. If you assumed Leo I was gravitationally bound to the Milky Way, you got a higher mass. If you assumed it wasn't, the estimate dropped.
So the results were sensitive to which tracers you included and assumptions about them being bound.
Yes, and again, small sample sizes and the lack of precise, proper motions for many of them were significant hurdles.
You also mentioned something called the timing mass method. How does that work? It sounded different.
The timing argument. It's quite clever. It treats the Milky Way and Andromeda, our big neighbor, as basically a two-body system. The idea is they started close together after the Big Bang, moved apart with the universe's expansion, but their mutual gravity has been slowing that separation down.
Right.
So if you measure their current separation, their relative velocity towards each other, and you know the age of the universe, you can calculate the minimum total mass they must have to explain their current state.
So it gives a constraint on the combined mass.
Primarily an upper limit on the combined mass, and by extension, an upper limit on the Milky Way's mass. Pre-Gaia, this method generally suggested the Milky Way's mass was likely less than about 1.6 trillion solar masses.
Interesting. So pre-Gaia, the Halo star studies gave maybe around 1.1 trillion solar masses, plus or minus a bit, which seemed to fit okay with that timing argument limit.
Broadly speaking, yes, there was some consistency, but also significant scatter depending on the method and tracers used.
And just to reiterate, all this mass we're talking about, the stars and gas are only a tiny piece of it.
A very small piece. If you add up all the stars and the cold gas, it's about 6 by 1010 solar masses. Maybe bump that up towards 9 by 1010 if you include the hot gas corona around the galaxy.
So compared to a total mass of, say, 1.2 trillion solar masses,
Yeah.
that's tiny.
Yeah, it works out to only about 6 or 7% of the total mass, which is interesting because the universe as a whole has about 16% baryonic matter.
So the Milky Way seems missing some of its expected normal matter. Or rather, it has a lot more dark matter relative to its stars and gas than the cosmic average.
That seems to be the case, yes. It really highlights how utterly dominant dark matter is in shaping our galaxy's structure and mass.
Okay, enter Gaia. The Space Observatory has been mapping stars with insane precision. How did it change the game for weighing the Milky Way?
Fundamentally, Gaia's superpower is measuring those previously tricky proper motions, the tangential velocities for literally billions of stars, but also crucially for many globular clusters and satellite galaxies with unprecedented accuracy.
So it directly addressed that mass anisotropy degeneracy problem.
To a huge extent, yes. Having the full 3D space velocities for large samples of tracers allows for much more robust mass modeling. It has triggered a whole wave of new studies recalculating the Milky Way's mass.
Yeah, let's talk about some of those. You mentioned calling him et al. From 2019 using early Gaia data.
That's right. They used Gaia's second data release, DR2. They looked at 10 classical satellite galaxies like the Magellanic Clouds, Draco, and compared their measured 3D motions, thanks to Gaia, to satellite motions in sophisticated cosmological simulations called EGLE.
And by matching the real satellites to simulated ones.
They inferred a likely mass for the Milky Way. Their result was around 1.17 trillion solar masses, plus or minus about 0.2.
Okay, so falling kind of nicely within that pre-Gaia range, but presumably with more confidence. What about Fritz et al. In 2020? They used more satellites.
Yes, they used DR2 proper motions for a larger sample, 45 satellite galaxies. Using their kinematics, they estimated the mass within about 270 kiloparsecs to be roughly 1.4 trillion solar masses.
And extrapolating that outwards.
Led them to a virial mass estimate of about 1.5 trillion solar masses, maybe a bit higher than Collingham's result. Using more tracers potentially samples a gravitational field more thoroughly.
Interesting. Okay, different tracers.
Yeah.
What about globular clusters? Watkins et al. Used those with Gaia data too.
They did. They focused on 34 globular clusters in the inner halo within about 21 kiloparsecs using their DR2 proper motions.
So focusing closer to the galactic center.
Right. Within that region, they calculated a mass of about 0.2 trillion solar masses. then modeling how that mass likely extends outwards according to standard profiles.
They extrapolated the virial mass again.
Exactly. Their inferred virial mass was around 1.28 trillion solar masses, but it came with quite large error bars, partly because they were extrapolating from a relatively small inner region. It shows how the result can depend on where your tracers are.
Makes sense. And then came Gaia's even better data, EDR3, Wang et al. Used that in 2022.
Yes, Wang and colleagues used the improved EDR3 proper motions for a much larger sample of about 150 globular clusters. They also combined this with constraints from the Milky Way's rotation curve, how fast things orbit in the disk.
Okay, so multiple types of constraints. What did they find?
Interestingly, their results came out on the lower end of recent estimates. Depending on the exact mathematical model they assumed for the dark matter halo's shape, like a Zhao profile versus an Inosto profile.
Different ways to describe how dark matter density falls off with distance.
Correct. Their derived total mass ranged from about 0.54 trillion solar masses up to maybe 0.78 trillion solar masses.
Wow, that is quite a bit lower than the others we mentioned, like Fritz are calling them.
It is, and it really highlights that even with Gaia's amazing data, our assumptions about the distribution of the unseen dark matter still significantly influence the final number we calculate.
The source material you shared had a great plot summarizing a bunch of these recent Gaia-based estimates using different techniques. Distribution functions, genes, equations, rotation curves.
Yes, that visual really drives home the point. While the formal error bars on individual studies have shrunk thanks to Gaia,
The actual central values from different studies using different tracers or methods still show a noticeable spread.
they do. A value around 1 trillion solar masses, maybe 1.2 trillion, seems to be a common ground, but there's still ongoing debate and refinement. It reflects the inherent complexity of the problem and perhaps even the physical complexity of the Milky Way itself.
So, summing up where we are now, Gaia has been revolutionary, providing incredible data on tracer motions. We have tighter constraints than ever. A mass around 10,012 solar masses seems plausible, but it's not quite case closed.
Definitely not case closed. Gaia has given us huge insights, no question. But the total mass being so dominated by that dark matter halo is still, I'd say, relatively poorly pinned down.
Because we still don't fully understand the dark matter halo itself, its exact shape, its density profile, how lumpy it is with substructure.
Precisely. All those factors influence how tracers move and how we interpret those motions. Problems like the too big to fail issue, where simulations predict more massive dark matter subhalos than we seem to observe dwarf galaxies and show we still have puzzles to solve about halo structure.
So, wrapping up this deep dive, weighing the Milky Way is vital for cosmology, but it's tough because most of it is invisible dark matter. Gaia's data, especially proper motions, has massively improved things, leading to estimates clustering around, say, 1 to 1.5 trillion solar masses, but significant uncertainties remain tied to modeling that dark halo.
That captures it well. We've made huge progress, but the final answer is still being refined.
Which leads to a really fascinating final thought. Given how much we still don't know about dark matter, what it even is, fundamentally, how might a future breakthrough in understanding dark matter completely change the picture?
That's the big question, isn't it?
Could it totally reshape our estimates of the Milky Way's mass, its structure, maybe even our understanding of cosmic evolution itself? What new tools, what new physics might we need to finally truly put our galaxy on the scales? It's quite something to think about. Thanks for taking this deep dive with us today.